Yeah, absolutely.
Yeah. See, is this fine, right?
Yeah.
Hmm. You can see the cursor also, right?
Yeah.
Movement of the cursor. Yeah.
Mhm. We should start. It's 4:30.
Shall I start?
Yeah, maybe 1 or 2 minutes just to.
Okay.
Yeah, sure, ma'am. Sure, ma'am. Thanks.
Okay, so maybe good afternoon, everyone. So this sessions will be chaired by Kathakali. Kathakali is from JP Institute of Information Technology. So Kathakali, you can start.
Good afternoon, ma'am. Thank you. Good afternoon, everybody. Welcome to our post-lunch session. Before welcoming our next speaker, I would like to repeat few points. You can ask your questions by writing in chat box or YouTube comment box. Okay, I welcome our next speaker, Arvind S. from IIT Madras. Please share your always share.
Thank you, Kadakani. And I thank organizers for giving an opportunity to speak here. Um, okay, I'm going to speak on the construction of maximally entangled and entangling quantum evolutions, which is a joint work with Suhail Ahmad Radar and Professor Arul Lakshmi Narayan from the Department of Physics, Indian Institute of Technology, Madras. Okay, my main concern in this talk is about entanglement properties of the dynamics. As we all know, dynamics and kinematics forms an essential aspect of any theoretical understanding, and there is a nice connection in many times between the kinematical properties and the dynamical properties. Then the question about the entanglement nature of states, which forms the kinematical aspect, is very well understood and studied. In this talk and in this work which we have carried, we are interested to study the entanglement properties of dynamics and the construction of construction of maximally entangled operators and also the maximally entangling operators. Let's have some brief introduction. So the first one we are concerned here are the two measures of entanglement of operators. The first one which we are interested is maximally entangling operators. The quantity which is this is quantified from by the entangling power, which is the average entanglement produced by an unitary acting on the set of or ensemble of product states, which I'm going to explain in detail in the later slides. So this has the maximally entangling operator has many applications and in many different names in different areas. For example, it's called two unitary operators in quantum designs, and the state operator isomorphism implies that the existence of maximally entangling operators with maximum entangling power implies the existence of absolutely maximally entangled state. There is a four-party amaze states because of operator state isomorphism, and the same the two unitary operators or the maximally entangling operators has in another name called perfect tensors exist in the holographic literature. And next, the maximally entangled unitary operators, which is quantified by the measure of by measuring the operator entanglement, which again I am going to explain it in detail in later slides, which in recently has evolved in a new avatar called the dual operators. Why the duality is that the maximally entangled unitary operators acts on the many body system such that the transformation along the spatial and the temporal direction in 1 plus 1 dimensional systems is governed by the unitary transformations. And this property, what the authors call the dual operators, what they named it as the dual operators, which is nothing but the maximally entangled unitary operators, has found many very interesting applications in many body theory, especially because the calculation of correlation function in many body theory is very difficult, and this property of the operator being maximally entangled allow one to calculate the exact correlation function. In fact, actually what happens is that the correlation, because of this property of maximally entangledness, the correlations vanishes along inside the light cone, whereas the correlation lies only on the light cone, and which can be explicitly calculatable, which is with the exact form. That property allows one to characterize the many body system into its from its dynamical properties like interacting, non-interacting, and ergodic and mixing, etc., with just the properties of the unitary acting on the bipartite system. Even though unitary acting on the multipartite system, many body system, the many characteristics of dynamical characteristics can be obtained by, and classification is possible just from the unitary acting on the bipartite system. And recently, there are many other applications. I'm just mentioning the calculation of OTOCs, explicit calculation of OTOCs in many body systems, and the dynamics, and many properties in the many body theory literature. So the question is, what we are interested here is the how to construct such a maximally entangled unitary operators in any local dimension D. From here onward, sometimes I use the terminology dual, and sometimes I use the terminology maximally entangled, which is both, and which is what we carried out in this work along with Sohail and Professor Lakshmi Narayan. Okay. Before going in detail of the construction and other details, let's have some definitions which we are going to use in our study. First one is how do we define an operator entanglement? Let's define unitary in the bipartite Hilbert space, and whose Schmidt decomposition is given by this equation, where because of the unitarity lambda j by d square summing over all the lambda j's will be equals to 1, you can treat lambda j by d square as probabilities, and from that one can define the linear entropy as a measure of entanglement, and we use the linear entropy as the measure of operator entanglement, which is given by equation 1, and which is bounded by 1 minus d square, where d is the dimension, local dimension. This is our definition of operator entanglement. And next, another important quantity which we are interested is entangling power. Let's say that the bipartite system AB, and the unitary is acting on the product state, and it creates the and then what is the entanglement that it produces is measured. Let's say it's measured by linear entropy, and E of rho A is the entanglement produced by acting the unitary operator on the pure product state. An entangling power is defined as the average entanglement produced by an unitary acting on an ensemble of pure product states. Suppose this pure product state, the ensemble is drawn from the Haar uniform ensemble, then the entangling power has a simple expression in terms of operator entanglement of U and operator entanglement of US, where S is the swap operator. Okay, and there are other measures well studied, and most of them either relates to the Schmidt value, so one can directly calculate the Schmidt values from this one, And there are other measures which is not directly related to Schmidt values, but we are concerned here with the entangling power and the operator entanglement. Okay, so what is the main problem? We have phi AB, for example. This is the state expressed in the Schmidt decomposition, and the maximally entangled state can be obtained just by substituting. This is the mathematical construction. What I mean to say, by substituting lambda I, the Schmidt values equals to 1, which produces mathematically which will one able to construct the maximally entangled states, in the sense that the state's property is unaffected by what value of Schmidt, what the Schmidt value you are assigning to. But when it comes to unitary operator, the situation is not same, in the sense that the U has the maximum entangling operator property, that is 1 minus 1 by d square is the maximum operator entanglement it can reach, is obtained when all the lambda is equals to 1, but you cannot merely substitute this value into the expression and obtain the maximally entangled operator, because that will not preserve the unitarity of U itself. So that's that the first question which arises is when one is trying to study the what is the correspondence of entanglement in the operators. The first question is what is the maximally entangled operator and how do we construct such a maximally entangled operator. Well, so before going in details, again I need one mathematical requirement, what we call the realignment. So realignment is the reshaping of the matrix. For example, you can see this in a qubit case. For example, unity is 4 cross 4 dimension. So the realignment, is a matrix realignment, is matrix reshaping. For example, the first first block is reshaped into the first row in the UR. So this is which is a linear operation, which is a reshaping of the matrix. Okay, by using the property of some certain properties of the realignment, the Schmidt values are given by the eigenvalues of your Dagger. So then from that, operator entanglement takes a very simple form which can be expressed in the equation 8, and EUS which can be written in this very simple form, where U of TA is another matrix reshaping, which we all well know that the partial transpose on the first part, or partial transpose on A. So this is what expression it takes. So now the EU is maximum if and only if UR is unitary. That means the realigned operator also must be unitary. In general, it won't be unitary. It must be unitary. Then it has the maximum operator entanglement. And let's call this as a dual unitary. That's what the people call. And EUS is maximum if and only if the UTA, there is a partial transpose, is also unitary, and which we call them as a T dual unitary. And the EP is maximum, that is entangling power is maximum if and only if both UR and UTA is unitary, which is what in the literature is called the two unitary. That means given a unitary, suppose its realignment as well as partial transpose is unitary, then it is called the two unitary, and that gives the construction of two unitary operators, which is equivalent to say that the construction of four-partite Ame states. Okay, with these preliminaries, we are going to explain the construction of dual unitaries. The first of all, how to construct this dual unitaries, that means the maximally entangled operators. So we define a map MR as a nonlinear dynamical map on the space of unitary operators, which contains the two steps. For example, one is the R map, which we call, another one is a PD map. So what is the R map? R map is a linear map which takes unitary to its realign. That means it just reshapes its matrix elements. And the next step is the polar decomposition map, what we call the PD map, which takes any matrix or any operator to its closest unitary operator. So what is the closest unitary operator to X, which is given by its polar decomposition and the closest with respect to any unitarily invariant norm. When I say it's closest to any unitarily invariant norm is given by its polar decomposition. So now our map, the MR map, which we call the MR map, is given by, let us choose any unitary and then realign it, the matrix realignment, and take its closest unitary, which we call the polar decomposition, or take its closest unitary, and iterate this step continuously. And our claim, and we prove with some certainty, that it always leads to the maximally entangled unitary operators, and in fact it produces an ensemble of dual unitaries or maximally entangled operators. So what is, how is it working, and what is the intuition? Let's define Salis entropy in this form. And what we were able to prove is that, suppose the Q equals to half Salis, let's consider the half Salis entropy of operator entanglement, and we are able to prove that half Salis entropy is monotonically increasing under the MR map. So this is what we were able to prove, and the intuition can be explained with this simple diagram. The intuition is, suppose let's consider the circle represents the set of unitary matrices. Okay, and this is a pictorial representation. It's not the exact in any way, it's just a pictorial representation. It's a pictorial representation of the concepts. So the circle represents the set of unitary matrix. Let's choose u naught, and under the R map it throws the unitary matrix outside. That means the u naught R is not unitary. And now once you take the closest unitary to u naught R, it comes back again into the on the circle. That means u1 is now the unitary, and again you take in the next iteration you take it realignment, so it comes outside, it goes outside. So then you have u1 of R, and then again take the polar decomposition. That means what is the closest unitary to u1 of R, which is nothing but u2. Now the distance between u naught R realignment to its closest unitary goes on in decreasing. So what dn square defines is the distance between the realignment to its the closest unitary operator. So u naught of R to un, this distance you can see is goes on decreases, and very quickly its distance vanishes, and the realigned unitary operator realigned operator will become unitary, and that's where we obtain the dual unitary or the maximally entangled unitary operators. Okay, this can be more clearly is able to understand by using the 2-qubit case, where the complete character, that means local unitarily equivalent set of unitary operators are completely characterized by what is called the Cartan parameters, which is a 3-parameter family. For example, all this unitary or the 3-parameter family which completely characterizes the non-local unitaries or local equivalent unitary operators. And the space and it forms geometrically, it forms a 3 torus, but all the points are not uniquely specified. The points on the 3 torus is not uniquely specified by the non-local unitary. So one can define a subset of the values of of the Cartan parameters, so that one can define Weil chamber by restricting the Cartan parameter values, and from which uniquely what happens, this forms a tetrahedron in which every point on the every point in the tetrahedron uniquely defines the class of local unitarily equivalent class of unitary operators. So in this Weil chamber, dual unitaries or maximally entangled operators is the one C3 one parameter family. Other C1 and C2 are fixed, which is pi by 4 pi by 4, and then C3 can vary from 0 to pi by 4, the whole ensemble. And this right, the line of dual operators, these are the dual operators. And here we depict, so you pick any unitary from within this chamber, and what is the trajectory under the action of MR map. So what is the trajectory is what is clearly explained here. So you can see the few of them goes very fast. For example, if you pick any unitary from the base of this Weil chamber with a single iteration, it will reach us to DC naught. Some others will be slowly reach to the dual operators, which in detail we are going to explain next slides. So in a dynamical point perspective, dynamical systems perspective, what is it acting is that the dual unitaries, the maximally entangled unitaries, are the fixed points of MR square map. So you can easily see that suppose U is a dual unitary operator, then the action of R remains, keeps it as a unitary operator. Sorry, there is an error. UR2 is nothing but UR. So and then take partial this polar decomposition. Since it is already unitary, it retains its unitary property. So from that, one can easily see that the dual unitaries are the fixed points of MR square maps. And suppose these fixed points are attracting, and then there is a basin of attraction from which, if we start V naught, U naught will asymptotically close to dual unitary operators. Okay. So that's the intuition we made. With that intuition, we also studied some numerical examples. So the first one is for dimension d equals to 2. How quickly, suppose if you choose any dual unitary operator, this is a representative of two dual unitary operators. If one choose it, then for example, with a single step it will reach, and another one is some 2-3 just after 2-3 steps it will reach to the maximum. So almost in the dual case it will reach to the maximum by 20 or 30 steps. For example, in dimension d equals to 3, it reaches within some 50 or 70 steps. And also you can see the difference between the maximum, so it will goes to 10 to the power of minus 20, 25 and all those. It's a very small, it's very close to the dual, numerically very close to the dual operators. And these are all for higher dimensions. For example, the same plots, in the sense that the growth of linear entropy under the action of the MR map, you can see that how quickly it is becoming a dual unitary operators. We have studied up to, you can see up to the dimension d equals to 7. This is the growth of the operator entanglement. And we were numerically able to check that the majorization relation, for example, u1 of r plus and u r n plus 1 is majorized by u1 r plus and u1 r. That means that the entropy of u of n plus 1, any entropy is greater than or equals to u n, except certain cases, especially in d equals to 3, that to the case of orthogonal matrices, which is of measure 0. But otherwise, in most of the cases, we were able to see the numerical justification for this majorization relation. So we conjecture that this holds except few cases. Okay, then the question is that whether this map also produces the maximum entangling power. Then the question is, one can see the distribution of entangling power under the MR map. So in the maximum that it can reach under dimension d equals to 2, it cannot reach the maximum, whereas d equals to 3, you can see a very small amount, a small line, green line at the maximum. very small line. So the very small fraction of the dual unitaries is also becoming two dual unitaries under the map. Whereas dimension d equals to 4 and 5, you cannot recognize that. So then the question is that, can we modify slightly this map and produce the two unitaries? There is the maximally entangling operators also. So we modified the map, what we call the MTR. So now, similarly, let's consider the U0 is any unitary, and first do a realignment and then take a partial transpose on the realigned unitary operator, realigned operator, and then take a closest unitary operator to closest operator to UTR, and repeat it iteratively repeating this map, MTR map. You are able to see the increase of entangling power, and we can numerically see that. So this is the blue color one is a CUV distribution of entangling power distribution of CUV, and then the green one. See, for example, for dimension 3, almost all of them have already reached the maximum. Very small fraction lies around 0.45 or something, but almost all of them reaches to the maximum for dimension d equals to 3. Thereby,
Aravindo, sorry to interrupt. You have 5 minutes left.
yeah, thank you. So it produces an ensemble of very huge ensemble of two unitary. There is maximally entangling unitary operators, and for dimension d equals to 4, there is local dimension 4. It also produces some two unitaries. You can see that the distribution. Whereas for 5 and more than 6, we are not able to see any production of any two unitary operators. Well, thanks. We are at that time of concluding. So we have what is the contribution is that we have introduced a nonlinear map in the space of bipartite unitary operators whose fixed points are attracting and have generically maximal entangling properties, which produces an ensemble of dual operators in all local dimensions and two unitary operators in smaller dimensions. So then there are many open questions. For example, the many attractors and basin of attractors of these maps remains open, as it for example, this itself as a from the dynamical systems perspectives, there are many interesting open questions exist. And from the many body systems properties, for example, there are many other quantities needs to be studied, and the relation of other entangling properties to complexity and the nature of dynamical evolution and ergodic properties need to be studied. We are in the process of doing this work. And then the what happens if to extend this understanding to multipartite system, and when the local dimensions are not equal, that is unequal dimensions, is also one of the open question, and we are into it. Okay, thank you. Thanks for
Thank you, Aravindo, for wonderful talk. There are some questions from audience.
yes, can you be a little louder?
Yes.
Shall I?
Audible?
Yeah.
The questions are, the set of unitary matrix, is it convex in all dimensions?
No, I am not able to hear. Kathakali, little bit louder.
The set of unitary matrix, is it convex in all dimensions?
No. No, it means adding two unitary operators, convex combination of two unitary operators is not unitary.
Okay. Another question here: how you define dual matrix? Do these exist in dual Hilbert space of operators? It is for KK Sharma.
Dual Hilbert space, I don't know what does it mean. Here I am just defining dual unitary operators are the one which has the maximal entanglement, or having maximal operator entanglement. So that's what I mean when I say the dual unitary operators, or in other words, why the dual name is that when they are using this many body systems, the evolution along the time direction, for example 1 plus 1, here you have a spatial system and many body system, and along the vertical dimension you have the time evolution. Now the evolution along the time axis and evolution along the space axis both is governed by a unitary matrix, unitary transformation. So that is why they use the term called dual, which allows one to explicitly calculate the correlation functions in many body theory. So that's where this word unitary comes.
And from Ujjal Sen, do the fixed points change if we start off from non-maximally entangled initial states rather than product states?
No, there was a
You
disturbance
can
in
see
it.
your chat box also.
Where is it? Wait. Yeah. 1 minute. Uh, do the fixed points change if we start off from non-maximally entangled initial states rather than product states? Sir, do you mean by non-maximally entangled initial states when you are? I'm not getting it. Fixed points if we start off from the non-maximally entangled initial states, that means the unitary operators.
Yeah, I thought that you are always initially acting on the initial state of your unitary. The entangling unitary is always a product state, right?
Yeah, that is the way we define this entangling power. Entangling power. Power
Exactly.
is defined.
And then on this nonlinear map has a fixed point in the space of unitaries.
Yes.
But suppose you take the initial state to be an entangled state and still take the final state as entangled and define the entangling capacity to be the distance, difference between the two entanglements, will the fixed point change?
No, it remains same. It again gives the maximal entanglement.
Okay.
I believe that.
Thank you.
Yeah, I meant to ask that picture of circle. Yeah, okay. No. That picture of circle is just pictorial. It has nothing to do with the exact mathematical representation. In order to convey our proof in a very simplistic way, I used that the circle as a unit. In fact, that circle is also because the all the eigenvalues lies on the circle. So that's why we used the circle. For example, for the unitary matrix, all the eigenvalues lie on the unit circle. So that's why we used that circle to represent the unitary matrix. That's where the last question, if I understand correctly.
Okay, thanks,
So,
Arvinder.
just one small question. So, Arvind, why do you say your operator is nonlinear?
No, not the operator, the map. The map, MR map, which we defined, because the map contains the two steps. One is realignment, which takes the unitary operator to some other realignment operator, which is a linear. Sorry. Whereas some disturbance. Okay, so whereas the another step, which is called the polar decomposition, taking any operator to its closest unitary, is not a linear operation, which is a nonlinear operation. So that is the reason we call this the map is a nonlinear map.
Is there any other question? If not, then thanks, Arvind, again for your wonderful talk. So I would like to welcome our next speaker, Saronath Haldar from HRI. Saronath, please share your. Hello, Saronath, are you hear me? Can you hear me?
Is it possible to hear my voice?
Yes, yes, you are audible.
And my screen?
No, no,
Not yet?
no.
It came and then went. So
Yes,
yeah,
now it's.
Ah, okay. So I
please make
thank.
it full screen, Sharonath.
Yes, 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 sure. Wait a minute, how to do
No,
this?
no, that is there. Exactly there. There is a full screen. Just up. Yes. Click on.
No, somehow it is not happening here.
Click on the box. Click on the box.
Click on the box. The same place. Click on the box. Yes. Is there any problem?
Yes, yes, somehow I'm experiencing some kind of problem here.
Okay, it's fine. I think it's not so much disturbing if you can make it.
Yeah, we can see your screen, so you can go like that now.
Yeah, it's fine. Absolutely fine. Go ahead.
Okay, okay, all right. Okay, so I first thank the chairperson for the introduction, and I'm also thankful to the co-organizers. They have worked very hard to make it happen, and I'm also thankful to the faculty members of the advisory committee. Okay, so now I'm starting. I'm talking about locally distinguishing quantum states with limited classical communication. This is a recently published paper appeared in Physical Review A. I have written this paper with Chirag Srivastav. Okay, so this is the outline of my talk. First, I'm going to talk about state discrimination problem. Then I'm going to talk about local operations and classical communication. Then there are several settings which has been considered in this particular problem. So I'm going to talk about different settings. Then considering all those settings, the present results will be discussed, and then I'll draw the conclusion. Okay, so the definition of state discrimination problem without considering whether the given quantum system, whether it is joint system or some composite system or single quantum system, in general, state discrimination problem can be defined in a way that the given quantum system is being prepared in a particular state. That particular state is taken from a known set. So clearly the information regarding the set is known to the party or the parties. Okay, the task is to identify the state by performing some measurement on the quantum system. Now, based on the type of states given in the quantum system, one can go for different types of strategies like perfect discrimination, probabilistic discrimination, etc. Now, the problem may occur when a composite quantum system is distributed among several spatially separated parties. Why it can be a problem, I'll discuss that. But before, I want to mention that in most of the work we have actually considered two-party system. So there are two locations, location 1 and location 2, and these two locations are spatially separated. Now, in a spatially separated paradigm, it is important to talk about this operation LOCC, which is regarded as free operation in entanglement theory. This LO part is basically the operation acting locally in a single location. So this is basically the problem, because when within a composite quantum system, the particles are basically distributed among several locations. then the operation cannot be conducted on the whole quantum system. So it is basically providing some kind of restriction. Because of this restriction, problem may occur. Now, the CC part is basically the abbreviation of classical communication. The CC part is usually used to make strategy. So I always actually use this type of examples where the four quantum states are given. So a 2-qubit quantum system is being prepared in one of the states, secretly chosen from this set of 4 states. Okay. Now you see in the Alice's side there is only one type of measurement is possible, and one type of measurement is possible, that is measurement in 0-1 basis. Now if Alice gets 0, then the outcome will be conveyed to Bob, and based on that measurement outcome, Bob can measure in 0-1 basis. In this way, it is actually possible to identify the state of the system. Whereas if Alice gets 1, then accordingly Bob can actually choose a plus minus basis. So here the changing the basis is basically represented as making strategy. So this is based on classical communication. Now, why this local state discrimination setting is important? There are many applications of this local state discrimination problem, but particularly I am interested in studying non-local behavior of a distributed quantum system, because in this particular direction, this local state discrimination setting is very effective. For example, one can consider that there is a famous paper, Quantum Non-locality Without Entanglement, and due to that paper, the authors have considered local state discrimination setting and discovered that there exists a class of operations which is known as separable operations, that is basically a stronger class of operation compared to LOCC. So this type of behavior, to explore such things, it is highly important to consider local state discrimination problem. Now here we are going to consider a limited case, considering limited communication. Means if there are parties, then the parties are not allowed to communicate whatever they want. There are restrictions on the classical communication as well. So it is known that non-orthogonal states cannot be perfectly distinguished. But even if the states are orthogonal, as I said, if the particles are distributed among several spatially separated parties, then there might be problem when the parties are going for LOCC, because there are many examples where it can be shown that even if the states, possible states of the system are basically orthogonal, still it is not possible to identify the state of the system via LOCC. But you see, in principle, as long as the states are orthogonal, conducting some kind of global operation, it is always possible to identify the state of the system. So from that point of view, global operations are basically much stronger operations compared to LOCC. So we are considering here a more complex situation because the CC, classical communication part, is limited. As long as there is limitation on classical communication, we want to look if it is possible to compensate by allowing the parties pure entangled states as resource, or maybe multiple identical copies of the states to be distinguished. So there are several settings we have considered. Particularly, we want to mention that in throughout the work, we have considered LP, local projective measurements, not even general class of local operation. One may, in fact, we in many cases, we have not allowed classical communication during local projective measurement. So as a result of which, the class of operation we have considered is experimentally friendlier. So this is one of the motivation of the present work, and subsequently we explore some other motivations as well, why we want to conduct this type of studies. I mean, exploring this weaker class of operation compared to LOCC in state discrimination problem. So please remember that this LP without CC, we simply say this as LP. And if it is not possible to accomplish some task by LP, then some additional resources will be allowed, as mentioned earlier. This can be pure entangled state or multiple identical copies of the states to be distinguished. So there are some other important things. We are going to talk about something which is called incomplete teleportation based protocol. This particular term has been taken from the existing literature. There basically authors have argued that one EBIT of entanglement and one CBIT of communication is allowed. This communication is from Alice's side to Bob. So compared to standard teleportation protocol, where one EBIT of entanglement is allowed and two CBIT of communication is allowed, we say this as incomplete teleportation based protocol. Both probabilistic and perfect discriminations are considered in this particular work. It will be mentioned accordingly. In case of probabilistic discrimination, remember that minimum error setting is considered. Minimum error setting can be, the error can be minimum with respect to particular protocol. So in few cases, we cannot say about the optimal probability of success. Okay, so I'm starting to talk about the results. First, I'm considering the states of equation 1. This example has been introduced in the literature by Grossman and Vedman in 2001. This is a nice example where one CBIT of communication from Alice's side to Bob is sufficient when LO is there, local operations are there to distinguish the states perfectly. But if CC is not allowed during local projective measurement, then success probability is about 0.85. Now, to make it perfect discrimination, one EBIT of entanglement is necessary and also sufficient. It is actually known. This is due to Grossman and Resnick, published in 2002, Physical Review A. Now, the protocol can be accomplished in this particular fashion. Alice's and Bob's bases are given. Somehow, here we have ignored the normalization condition. This normalization coefficients are basically 1 by root 2. Okay, now theorem 1. In theorem 1, we have basically explored a class of non-maximally entangled state A00 plus B11, this type of non-maximally entangled state. And we have asked the question, if this type of non-maximally entangled states are given to Alice and Bob to distinguish the states of equation 1, as I have already shown, what will happen? What is going to be the success probability if they stick to minimum error discrimination setting? So we have explicitly calculated the success probability in this case, and which is basically 3 by 4 plus half into curly n. This curly n is equal to AB. Please remember that here we have taken AB as real. So this is basically the negativity of the resource state, and it can be easily shown that if AB is greater than 0.2, then that non-maximally entangled state can be actually useful to have success probability going beyond 0.85, which is basically under LP only, when there is no maximally entangled state or there is no entangled state. it is possible to generalize these results in this particular fashion. Due to Walgett and Hardy, it is actually possible to consider the structure of any 2-qubit product basis, and in this case we have considered what is going to be the success probability, provided that we have modified the protocol a little. In particular, instead of Bell basis, Bob is basically performing measurement in some entangled basis. Now, this is the expression of the probability of success. Remember that in this case, maximally entangled state is being considered as resource. So one may ask, what is the importance of this particular work? We have to remember that the above probability of success is particularly important because there is no known protocol till date which works perfectly for any values of alpha. Okay, now theorem 2. In theorem 2,
पढ़े थे जो हाथ में ले रही तो हाँ इसे पढ़े थे.
In theorem 2, we have considered any 2-qubit product basis, and we have we have actually proved that 2 copies are sufficient to distinguish such states when only local projective measurement, that is LP, is considered. Please remember that these copies are allowed, given to the parties one by one. It means that when all the measurements are performed on a particular particular copy, then the other copy will be provided. So this is basically the corresponding protocol to identify the state of the system correctly. So so far we have already told that using entanglement, even if it is maximally entangled state, it may not be possible to identify the state of the system perfectly when arbitrary alpha is there. Arbitrary alpha is there when the given set is basically arbitrary 2-qubit product state. But we have seen that when 2 identical copies of the states are provided, even if those copies are provided one by one, it is becoming effective one to identify the state of the system correctly. So we are concluding here in this particular scenario, identical copies as a resource is becoming very effective for product state discrimination under LP without CC. Okay, now theorem 1. In this theorem, we have considered the discrimination of 3 or 4 Bell states, which was conducted before via LOCC and SAPE, that is separable measurements. Now, when the non-maximally entangled state A00 plus B11 is given as resource, what is the optimal success probability under LOCC or SAPE to distinguish 3 or 4 Bell states? It was actually known. Here we have proved that to achieve that optimal success probability, one need not to go for LOCC or separable measurements, these stronger classes of measurements, where we have proved that local projective measurement is actually sufficient. And the corresponding protocol is given here. Step 1, that is subspace discrimination by both the states, and state 2, due to this subspace discrimination, some kind of non-orthogonality will occur, and that non-orthogonal states will be distinguished probabilistically by Bell measurement. Now here comes a very important thing. These optimal probabilities for 3 or 4 Bell state that can be achieved under LP, which is a weaker class of operation. So this is one of the strong motivation that we find eventually, that it is important to identify those scenarios where actually the task can be accomplished using a weaker class of operation or experimentally friendlier operation. So this is a motivation of the present work, that if we shed light on the weaker classes of operation, then we will be able to explore that where such operations can be cost effective. Okay, so next we consider perfect discrimination of three orthogonal quantum states. In case of in case of this particular scenario, one can consider two of the three states as Bell states, and the third state could be any state which is basically orthogonal to the previous selected two Bell states. Now, under this situation, to distinguish this ensemble.
Ronald, you have 5 minutes left. You have 5 minutes left.
Okay, all right. Okay, so LPSE is sufficient to accomplish this particular task. This LPSE is basically local projective measurement and shared entanglement. Here, shared entanglement is basically maximally entangled state. So in this case, one can actually avail previous protocol. Now remember that in case of previous protocol, we have considered non-maximally entangled state, and here we are considering maximally entangled state. And because of the usage of maximally entangled state, the non-orthogonality will not occur, as a result of which perfect discrimination is possible. Okay, so incomplete teleportation based protocol, I have already mentioned why this is incomplete teleportation based protocol. I just want to mention the result. If any three states of the above of these four states are given to Alice and Bob, provided that Alice and Bob know which three states are given, then these three states can be perfectly distinguished under incomplete teleportation based protocol. I'm skipping the protocol, it is given in our paper. Now the last theorem, in this theorem we have proved that given any orthogonal product basis, it is actually possible to distinguish this product basis when a finite number of identical copies of the states are given. Provided, it is not at all important that what is the total dimension of the system, or what is the dimension of the individual subsystems. This is actually happening because in case of product basis, the states basically maintain orthogonality with respect to some party site. So this is why LP actually can help. So setting is like same, copies will be given one by one, but it may not be possible even if there are two entangled states. So to conclude, here we have considered limited communication, that is restriction on classical communication. So we have, in this way, we have tried to explore what is the role of CC, or in some cases where exactly it is possible to identify weaker class of operation as optimal. To compensate, we have used resources like entanglement in pure form or multiple identical copies of the ensemble states. So we have seen that for product states, these identical copies are basically playing an effective role, whereas for entangled states, entanglement can be effective. So for entangled states, we have identified a type of indistinguishability under the local projective measurement in many copy scenario, which will never actually occur for product states, because product states can always be distinguished perfectly under LP when multiple identical copies are given. Some open problems are there, like it includes in few cases we have not found the optimality of the success probability, so one can look for these things. And obviously it is important to explore more regarding weaker classes of operation, and also to explore the role of CCs in different information processing protocols as well. So we are thankful to Professor Ujjwal Sen for his valuable comments, based on which the paper was improved significantly. Thank you.
Thank you, Sarnath, for wonderful talk. There are some questions for you.
Yes, of course.
Question from Ribhu Gupta. In case of KELO without CC, would POVM be more useful than PV? That is, can they increase the success probability? You can
Yes,
see the question in chat box.
it can be possible, but the thing is, such explicit scenario have to be constructed. Otherwise, it is not possible to argue whether POVM is working better than local projective measurement or not. But somehow in this particular direction, I mean, replacing CC by some kind of resource, there are very few papers. So to my knowledge, I haven't found this type of things yet, but it will be very interesting to look for.
Another question for Aravinda. If I impose super selection rule as the restriction, do you see the modification in the local distinguishability? I think yes. Can you comment on this?
What do you mean by super selection rule?
Aravinda, can you?
Saranath,
Yes.
some super selection rule, for example, some of the unitaries are not applicable in standard. This in the fermionic sector are those are other words use the Fox space based bosonic communication, or photons, for example, use the photons where the number of photons is conserved, for example. That is,
Recently, I have seen few papers. For your information, I want to tell you that this regarding this fermionic states, people are trying to distinguish those states under LOCC. Okay.
yeah,
So
yeah. Similarly,
discrimination
for
type of
example,
things, people have already considered, but there people have already observed that distinguishing those fermionic states even more difficult task respect to the results already reported in the literature of quantum information. Okay, so it can be interesting, but it's really very difficult to say what will actually happen, because unless some explicit mathematics are there, it's difficult to make a comment. Okay.
Any other questions? If not, then thanks the speaker again for your wonderful talk.
So, Kathakali, it was a pleasure having you as a chair.
Thank you, sir.
I think we thank the speakers of this session, and we switch to the poster session now. I think Arun Sherawat will take over.
Okay. Thank you, Professor Ujjwal. Maybe, I mean, should we start? Right?
Yeah, we can start. We can start with the first speaker.
Okay, so I will go, in the order which is given in this final UQ schedule. And so I will, there is a 5 minute for talk, and then 2 minutes for discussion. So when there will be 4 minutes, I will tell you, and then you can take 1 more minute to conclude. Okay. So the first speaker is Arnab Sarkar from IIT Kanpur. You can share your screen and tell us.
Hello, can you hear me?
Yes.
Hello. So, and you can see my screen also, right?
Yes.
Okay. So, good afternoon. I will talk about giant tunable mechanical nonlinearity in graphene silicon nitride hybrid resonator. So, this poster is totally based on this recent publication from our lab. The title is also same. So, the key question of this work is that if we have a linear large area oscillator, large area comparable to what I will explain, So if we have a large area linear oscillator, and if we can couple, or if we can switch in or switch out, and we can connect another tiny nonlinear resonator with it. So whether using this tiny nonlinear resonator, we can make this linear resonator nonlinear. If yes, then how much the nonlinearity is? Okay, to answer this question, first let us explain the sample we have used. So this gray large area surface, this is a silicon nitride surface. So and these black dots on it, these are single layer graphene surfaces, single layer graphene resonators, which are suspended on two holes of the silicon nitride. So we look at this sample is kept in a capacitive setup. So we can put a gate voltage on, and we can change the tension on the surface. And we probe the system using confocal microscope, and we send laser. And the reflected signal, we send it to spectrum analyzer, and we look at the spectrum. So here you can see this is a cartoon picture of the spectrum. So here these silicon nitride modes are the quality factor of silicon nitride modes are much higher than the graphene mode. So you can see these blue, red, or green peaks. These are silicon nitride modes, and this gray peak is the graphene mode. And if we put force on the silicon nitride modes when the graphene mode is not overlapping, so when these are not coupled, so we see if we increase the amplitude of the force, the response increases linearly. But when we tune in graphene, and now these modes are hybridized with the graphene modes, and we see this response becomes nonlinear. The question is that how much nonlinearity is it? So to answer this question, let me explain another scheme of this experiment. So suppose there is one silicon nitride, particularly one silicon nitride mode, which is coupled to the graphene mode. So they are strongly coupled. So you will see two hybridized mode 1 and hybridized mode 2. So suppose the frequencies are omega 1 and omega 2, and we are driving the system at omega p, which is omega 1 plus omega 2. Now what will happen, if we increase the pump power slowly, we will see initially parametric amplification of the modes, and then above threshold we will see the amplitude of the amplitude become very large, and then they start mixing. Through four-way mixing, we will see the frequency comb appear. From the frequency comb, we can calculate the nonlinearity of the sample. So now we want to model the system using one nonlinear equation is coupled to a linear equation, and the simulation results matches well with the experimental result. Now this part we have seen on graphene surface, and we can calculate nonlinearity of the graphene mode.
You
now,
have 1 minute left.
Yeah. So now we go on the silicon nitride surface. Now you see, we can see the frequency comb is induced on the silicon nitride surface also, and that is not only around the small tiny graphene drum, but everywhere on the surface. So these are the frequency comb at different distances, and from this frequency comb we can calculate the nonlinearity again, and this nonlinearity appears to be giant. So I will conclude my presentation here. So the nonlinearity of a low mass small size oscillator can be induced in a large area oscillator through mode coupling. Nonlinearity is estimated from the frequency comb generated through parametric amplification of hybrid modes. In near future, this experiment can be expanded at low temperature using high quality factor oscillator, high quality factor silicon nitride oscillator for quantum information processing. Thank you for your attention.
So I cannot see any question, but please feel free to ask if somebody have some question.
Well, I wanted to ask something. So is it when you model the nonlinearity, so the coupling constant for that, do you fit it with the experimental data, or do you have an independent theoretical value for that number?
No. Initially, so you can see this curve, this dotted curve. So we have when they are coupled, the graphene oscillator and the silicon nitride mode are coupled, we will see this hybridized mode, and we can fit. So this fitting curve will give us the coupling value. So that value we use for for the module.
Yeah, I had one small question.
Yeah.
Can you hear me?
Yeah.
I just wanted to ask, like, if you have a frequency comb of this kind, can you also couple it to some external light?
This is actually microwave frequency comb. So you can see these are megahertz frequencies. So I mean.
Yeah, I mean, can you connect it to some microwave light and get some kind of light matter interaction?
I have not. I mean, yeah, it is possible. I mean, I have not thought about it very.
Okay, yeah, thanks.
Okay, so I guess thank you very much, Arnav. And now we move to next one speaker, Sumit Mukherjee from NIT Patna. So Sumit, you can share your screen.
Yeah.
And
Am I audible and visible?
Your screen is not on, but you are audible.
So I haven't shared my. I'm just sharing that.
Okay, it's up now, so you can start.
So is it visible?
Yes.
Now
it's visible. You can start.
Now it's full screen, right?
Yep.
Okay. So thank you to the organizer for giving me such an opportunity to present our work here. So the title of the poster is that persistence of quantum violation of macro realism for large spin even under coarsening of measurement times. There are several words which can be known or unknown to us, and I will describe what they are. So there is a natural means quantum mechanics is gives some visual phenomena. So we though I should not mention like classical one and quantum world, I cannot categorize it like this, but this will be helpful for our further discussion. I just categorize this classical world and quantum world by some sort of rules which govern this world. So you can see them that like classical world is given by some state is given by some space points, and here some quantum world, here we use Hilbert space and quantization, Schrödinger equation. There it is Newton's law. So these correspondence, some question arises that whether this correspondence means that classical world is subsequently different from quantum world, or if it is so, then when a quantum system stops behaving quantumly and starts behaving classically. The second question is very interesting, though I think that this not the question, but even the existence of such a question is debated over the years. So our investigation is in that way. So in this regard, a famous quote by Arthur Perez is worth noting, that there is nothing in quantum theory making it applicable to 3 atoms and inapplicable to 10 to the power 23. This is what quantum mechanics is, because quantum mechanics do not tell about the dimension or any kind of spatial properties about the system. It is a tools for calculating the probability of certain outcomes given by Bond rule. But our goal is to classify some endophysical system and exophysical system, some system which obeys some sort of theory, like our investigation should be in that direction. So some sort of system, can we classify them by quantum theory? So here our work is based on what is called macro-realistic views, which is given by Professor Leggett and Gard. The views are given here. That is, some system exists independently of your measurement of macroscopically distinct quantum states. Macroscopically, here I have written macroscopically distinct states such that all its observable properties have definite values. So it is an assumption. And second assumption is that without affecting the system, you can actually in principle determine which state it is in. So this macroscopically, you can see that I have marked it in red color, that macroscopically distinct states. What does it mean? Whether it is a classical state or it is a quantum state? It is a very essential question to ask here. So Leggett, in very occasion, he has mentioned that it is actually macroscopically distinct quantum states. And you can see that this macro-realistic view, it is in principle, it is not somewhere equal to Bell's local realism, because it is a theory dependent. You are using quantum mechanics to.
You have 1 minute left.
Okay. But one question arises: if these macroscopically distinct quantum states, they are distinct in microscopic level, but it is not distinguished in macroscopic level. It can be possible. So this question was addressed by Bruckner et al. So that is called coarse-grained measurement, where you have microscopically distinct state, but for some indeterminacy in measurement apparatus, you cannot distinguish them. So you can just club the outcome and investigate further whether it is behaving quantumly or classically. So it is called coarse-grained measurement. So we asked a further question that not only the final measurement outcomes resolution, but what if we also coarse-grain the measurement reference, which in our case, when we investigate Leggett-Gard inequality, in our case, this measurement reference is time. So we coarse-grain the measurement reference also and investigated what is coming. So this is some probability calculation rules. So the first two are for coarse-graining of measurement outcome, and second one is what is the measurement reference coarse-graining. That is of time. So here is the detailed calculation of that.
You have to conclude fast because.
Yeah. So here is the table for violation of different inequalities. Wigner form of Leggett-Gard inequality and no signaling in time. I forgot to mention that. So this is the graphs we got. So the main conclusion from here is that even if you coarse-grain your final measurement resolution, and even if you are coarse the measurement reference, quantumness can still be there. Means we have got the violation of these inequalities. So some sort of quantumness is even there. So quantumness persists. And one previous result was that when you are coarsening over the measurement reference, you are getting classicality. So our result simply contradicts their result. Those results are by Jeong et al. I have given that reference at last. So, but there is a reason between the for the apparent inconsistency.
I have to stop you because you are running out of time. So I mean,
okay.
So I think we have to move to next talk. If there is no question, I mean, I can quickly add one question, and that's all.
So they are my co-authors, Anik Rudra, Devarsida, Shiladitya Da, and Professor Dipankar.
I have a quick question that when what is the maximum J that you find which gives you the violation, and what will be the amount of violations with J?
Yeah. For the half integer spin, we have calculated for 33 by 2, J equals to 33 by 2. And for integer spin system, we have calculated for maximum J equals to 15.
No, and what will be the trade-off? Like violation amount, will it decrease with J or what will happen?
Yeah. You can see from here that violation of with the increment of spin, you are getting just greater violation. This is a trade-off. Yeah. If we are going from less spin to upper spin, so you are getting more violation. But the more or less the nature is that violation is decreasing as your sharpness of this coarsening is less.
Okay, thank you.
Okay, so thank you so much, Sumit. And now we move to next one. So next one is Anu Kumari from DTU Delhi. So so she can. So Anu Kumari, are you here? So. Okay, so you can start. I mean, I cannot hear you.
Oh, okay, sir.
Oh, okay. Yeah, I can hear you. I can see your screen. You can make it full screen and then you can start.
Good evening, all. The title of my today's poster presentation is Detection of a Mixed Bipartite Entangled State in Arbitrary Dimension via a Structural Physical Approximation of Partial Transposition. The motivation of this work is since it is very crucial to check whether the quantum state generated in an experiment is entangled or not. So it's necessary to develop entanglement detection criteria which can detect whether the given quantum state is entangled or not. In the literature, most of the criterion are for same dimensional Hilbert spaces. Even some work has been done to detect entanglement in different dimensional Hilbert spaces, but they are not experimentally realizable. So we need to develop some criteria for detection of entanglement in different dimensional Hilbert spaces such that it be realizable. Our criterion is important since it can detect entangled states in different dimensional Hilbert spaces, and since our criterion is based on the method of structural physical approximation, and that's why our criterion is experimentally realizable. So in this work, we have proposed 3 different criteria for the detection of mixed bipartite negative partial transpose entangled states in arbitrary dimension. Since our criteria is based on the method of structural physical approximation, therefore it is experimentally realizable. Our 2 criteria is given in the terms of concurrence of the given state in arbitrary dimension. Lower bounds and upper bounds for the concurrence. So our first criterion detects negative partial transpose entangled states if and only if the average fidelity between the two quantum states described by rho and its structural physical approximation of the partial transposition of the witness operator is less than, where the quantity R depends on 2 things. First, the dimension of the composite Hilbert space, and secondly, the parameter that makes structural physical approximation partial transposition of witness operator a positive definite operator. So our first criteria may be stated as a bipartite D1 tensor with T2 dimensional quantum system described by a density operator rho AB represents a negative partial transpose entangled states if and only if trace of W tilde rho is less than R, where W tilde is given by equation second. Here W denotes the witness operator detecting rho, and the value of the parameter P should be chosen such that W tilde is a positive semi-definite matrix. That is, the eigenvalues of W tilde are non-negative. The second criteria tells us that the given state is negative partial transpose entangled if and only if the minimum eigenvalue of the structural physical approximation partial transposition of the given state is greater than or equals to the difference between the concurrence of the given state and the average fidelity of the given state and the average fidelity and its structural physical approximation. Since we are not able to find the exact value of the concurrence, we have given the upper bounds and lower bounds of the concurrence, and also our upper bounds and the lower bounds of the concurrence are given in terms of average fidelities, so they are experimentally realizable. Our third criteria also deals with the detection of entanglement. So,
you have 1 minute.
the bipartite state rho of an arbitrary dimensional in an arbitrary dimension is negative partial transpose entangled if and only if U entangled is less than half, where U entangled is given by equation 6. In our work, we have illustrated our results for a qubit-qubit system and a qubit-qubit system, but here I have taken a qubit-qubit system. So we have taken rho here, this which is represented by equation 7, and we have find out the conditions where it is entangled, and the conditions are given by equation 11. And the concurrence of the given state is given by mod f minus a. Then we have, since it is an entangled state, we must have an witness operator detecting it. So the witness operator detecting rho can be expressed by equation 13.
You have to conclude, I guess. You have not much time. So
Yes, we have verified our results for this state. So these are some values for which we have checked, and these are the references. Thank you.
So I cannot see any question. So if there is some question, I can ask quickly one question. So I
go
think
to the next one, and then later, if someone has a question at the end, people can also talk.
Okay, thank you, Anu. And we now move to next speaker, Shuryans Asthana from IIT Delhi. So please share your screen.
Yeah, so is my screen visible?
Yes, yes, you are audible and screen is visible. You can make it full screen.
Yeah, so first of all, I want to thank the organizer for giving me the opportunity to present our work in this conference. I will be talking about entanglement and steering inequalities from common framework, and the work is done in collaboration with Swami Adhikari and V. Ravishankar. So the basic motivation for our work is that we ask the question, what is the quantum representative for indicator function of two joint events? So as we know that in the classical domain, we can ask probability for any event which may involve incompatible observables as well in quantum domain. So if there are two observable A and B, and A takes a value small a and B takes value small b, so the probability of the joint event is obtained by first looking at the indicator function for this common support, and then taking the overlap of this indicator function with the classical state. But when we transit from classical domain to quantum domain, my indicator function map to projection operator. So the indicator function for A equal to A maps to a projection operator pi for observable A corresponding to eigenvalue small a. Similarly for observable B having value small b. But what will be the quantum representative of indicator function for joint event? Because A and B can be non-commuting as well. So we may employ the standard rules of quantum mechanics to find the quantum representative, and which is nothing but the symmetrized product of the two. So this operator we call a pseudo projection operator because it shares some properties. For example, it is a Hermitian operator, but it is not an idempotent operator. That is, pi square is not equal to pi, and it has negative eigenvalue, and that characteristic we treat as a signature of non-classicality. And if we have more than two observable, then the generalization is quite straightforward. Okay, there is non-uniqueness involved in that, but I won't go in that here. And pseudo probability can be defined analogous to our usual probability as the expectation value of this pseudo projection operator in the corresponding state. And since it has a negative eigenvalue, the pseudo probability can take negative values. So our definition of non-classicality is that a state rho is non-classical with respect to a set of observables if at least one pseudo probability in the scheme turns negative. That is, even one of the pseudo probability for joint events A1 equal to some value up to An equal to some value turns out to be negative. Okay, so since our definition of non-classicality is broad enough, so the question that we want to ask is how the criteria for different known facets of non-classicality which have been used as a resource, such as non-locality, entanglement, steering, they emerge from it. So for that we have used, I will present here the 3-qubit result. So basically the AI represents sigma dot AI. Okay, and all the directions make an angle small alpha with respect to each other, as has been shown in this figure. And this is the sum of pseudo probabilities that we have to take for getting an entanglement inequality. Now the question arises, what is the rationale underlying this choice of pseudo probabilities? So as we know that entangled states share correlation in more bases than one. So we choose our pseudo probabilities such that there are correlations in more than two bases that are involved in the final expression. Secondly, this is only for simplicity at the first step, that here we have chosen them such that all two body correlation and single body term, that is sigma I sigma j type of term and simply sigma I type of terms, they get cancelled. So if we put in the expressions for pseudo probability and demand the ensuing expression to be less than 0, that is the demand for non-classicality, we get this kind of entanglement inequality. Okay, now this inequality, if we do not restrict the value of alpha, it will detect all the separable states, some of the separable states also as non-classical. So the demand that
you have 1 minute left.
Okay, okay. So the demand that alpha, this inequality gets violated by separable state puts the restriction on alpha, and that is what I have shown here. Similarly, if we want to get nonlinear entanglement inequalities, we will have to choose appropriate combinations of pseudo probabilities and the product of them, such that the rationale will apply here as well, that the correlation in more than one basis is there in the ensuing expression. And when we put the demand that this is less than 0, then we get this entanglement inequality, and similarly the demand restricts the value of alpha. So the conclusion is that here I have shown the results only for entanglement for want of time. We have derived things for non-locality and steering as well. So we get the conditions for different paradigms of non-classicality from a single framework. Secondly, since Marginov-Hill distribution shares a relation with weak values, so we can simultaneously identify anomalous weak values that signify violation of classical probability as well as presence of a non-classical resource state. Thank you, sir.
Thank you. Um, so if there is some question, I cannot see any question. But those who are not speaking, can you switch off your microphone?
No, actually, Arun, you have to look at the chat box. Gautam has a question.
Okay, okay, okay. How does there's a question I can see. How does this pseudo probability compare with the Wigner distribution and other known quasi probability distributions? So
okay, so I can tell you the equivalence with the Wigner distribution function. If we look at the characteristic function, then Wigner distribution function is like e to the power I sigma xi plus tau I sigma xi plus tau some eta, and this the characteristic function for the pseudo probability distribution is symmetrized product, that is e to the power I sigma xi into e to the power I tau eta plus the hermeticized part of that. So that is the connection between the two. Classically they are one and the same, but quantum mechanically there are two branches. And since we know the relation of Wigner with P function and Q function, so with that knowledge we can relate it with P and Q as well.
okay. So if Gautam, if you have some more want to clear, I guess it's clear, or if not.
Yes, it's fine.
Okay, so I cannot see any more question. I thank you. Shuryans, thank you so much. And
thank you.
We move to next one speaker, Kornika from HRI. You can share your screen. Yes, it's visible.
So visible slides?
Yes, slides are visible. You are audible. You can make it full screen. Okay, so you can start now.
Everyone. Name of my poster is Beating Detection Loophole in Nonlinear Entanglement Witnesses. So entanglement witness is an operator which helps to detect entangled states. Like these are the set of separable states. Then according to the Han-Banach theorem, we can always draw a hyperplane which separates the set of separable states from some of the entangled states. This is the witness operator. Its expectation value is positive for all the states which belongs on this side. So it is positive for all the separable states and some of the entangled states like rho 1. And it is negative for all the states which belongs on that side. So it is negative for rho 2. So if trace of W rho is less than 0 for some rho, we can say certainly that rho is entangled. Witness operator for an NPPT state rho phi is given by this, where phi is the eigenvector corresponding to the negative eigenvalue of rho phi TB, where TB is the partial transposition over the second party. Now, if we bend this linear operator towards the separable states in such a way that it still doesn't intersect the set of separable states, then this nonlinear operator can detect more states than the linear one. Like in this picture, it can detect both rho 1 and rho 2. For this linear witness operator, we can make it nonlinear by subtracting a positive term from this, where psi is an arbitrary but fixed state and S psi is square of largest mid-decomposition coefficient. Now, to get the expectation value of the linear witness operators, we have to measure it. But if some loopholes are present in the measurement process, then the expectation value can become negative for a separable state. One of such loophole is called detection loophole. I will discuss this now. This is the measurement box. There are two inputs and two outputs, and let the eigenvalues should click one times, both of the eigenvalues. But due to the presence of the detection loophole, it may happen that one or more eigenvalues are clicking more than one times or less than one times. The first case is called additional events and the second case is called lost events. Accordingly, one can define additional event efficiency and lost event efficiency. Now, true expectation value of an operator is given by this, where ni is the number of time the corresponding eigenvalue lambda I should have clicked, and n is the total number of clicks. But this true value will be different from the measured expectation value, which is given by ni plus number of additional events minus number of lost events by n plus total number of additional events minus total number of lost events. Now one can see that this measured value is different from the true value. So due to this difference, the expectation value of the witness operator can become negative for a separable state, and the experimentalist may erroneously conclude that he or she got a entangled state. This detection loop was first considered by P. Square et al. In case of linear entanglement witnesses. I will not discuss that part due to the shortage of time. Those results were given in the poster. We have considered nonlinear entanglement witnesses. This nonlinear part can't be measured since it's not Hermitian, but we can decompose it in as a sum of two Hermitian operators. Now, to get the measured value of this operator F, we have to measure three things, W, H, A. Now, considering the effect of detection loophole, in all these three measurements, we got this new bound on the measured expectation value of the linear part of the witness operator. Now, by considering a particular example of the nonlinear witness operator, we have plotted here this bound. A state is entangled when the corresponding point lie above this curved surface. That is, the experimentalist can surely say a state is entangled when the corresponding measured expectation value of the linear part of the nonlinear witness operator satisfies this inequality, this bound, where this is the efficiency of the lost events.
You have 1 minute or more.
This is the result. So please look at my poster available online for more information. Thank you.
Yeah, thank you so much. So we can take some question. So I cannot see any question. So I guess.
So I stopped sharing.
Okay, so thank you so much, Kornikar. And now we move to our next speaker, Sumit Rao from Visva Bharati University. So you can share, Sumit, you can share your screen.
Yeah, I'm audible, right?
Yes.
Okay.
Yes,
Yeah.
we can see your screen.
Sure. Good evening, everyone. Today I'm going to speak about genuinely non-local product basis and entanglement assisted discrimination. This is a very brief introduction to state discrimination, but I will conveniently skip it because it was discussed earlier today. So not all orthogonal states are locally distinguishable under local operations and classical communications. Base states are, the four base states are a prime example of it. But product states to exhibit such a feature, Bennett et al. In the work on tile UPV So it's this phenomena of in so this in the phenomena of non-locality without entanglement, that this C3 cross C3 tensor 3 UPB orthogonal product basis is locally indistinguishable. Uh, Not only that, it is also locally irreducible. By irreducible here, I mean none of the given a state, it is not possible to eliminate uh, uh, other states that are not given to you, any of those. So, on the using orthogonality preserving measurements, by orthogonal preserving measurements, I mean the the post measurement states remain orthogonal, uh, and so that further uh, uh, identification is possible. All right. This phenomenon they term as non-locality without entanglement. Haldar et al. In their letter proposed three qubit and three q-code product basis that is locally indistinguishable when the three parties are separated, and remains so even when any two of the three parties come together. So this they termed as genuine non-locality without entanglement. Additionally, this set of states in C3 tensor 3 remains irreducible even when two parties come together. Uh, Information theoretically, this corresponds to a set of separable measurements that cannot be performed unless all the parties come together. This orthogonal product basis, they termed it as strong non-local product basis. This brings us to genuinely non-local product basis. It's basically a set of orthogonal product basis that is LOCC indistinguishable across every bipartisan. Uh, so, although this set is locally indistinguishable when all the parties are spatially separated, it may be possible to that elimination is possible in this scenario. If it is so, it is categorized under type 1, else it falls under type 2. Further, if we even though it is not possible to eliminate any state, and when all parties are spatially separated, it may become reducible when some of them may come close. So if this happens, then it comes under type 2A, and else it is categorized under type 2B. So let us quickly go through a few examples we stated there in our paper. So this set in C4 tensor 3 is a orthogonal product basis, and it is it's a GNPB, but when all the parties are spatially separated, elimination is possible. And however, this set of states is it's not possible to eliminate it when all the parties are spatially separated, but local elimination is possible when some of the parties come close. However, for these two set of states, local elimination is not possible even when two of the three parties come close. These two states are in C3 tensor 3.
So okay. You have 1 minute left.
All right. Next we come to entanglement assisted discrimination of these kind of product basis. These two product bases are in C3 tensor 3. So for this set, two EPR shared between any two parties will suffice to discriminate the set. For this, we need another additional EPR shared between, say, the third pair, but it is required for 8 out of the 27 cases. For this set, I discussed local elimination was possible when all the parties were spatially separated. So after the elimination, depending on the measurement outcome, only one EPR is required. For this set, one GSG is distributed between the three parties along with an EPR set between any of the two parties will suffice to discriminate the set. Uh, these are the results. And to conclude, we have studied genuine local product basis and showed it how elimination affects the amount of entanglement used for discrimination, and the orthogonal and we also discussed entanglement assisted state discrimination protocol that are efficient over teleportation, and also we addressed a open problem left in this letter and addressed in this letter, and so these are the co-authors who contributed to this paper, and thank you for your attention.
Thank you so much. So I can take one question if anybody have.
So should I stop sharing?
Yeah, I think no one have questions. So
all right.
Okay, so thank you, Sumit. And now we move to our next speaker, Ahana from HRI.
Can you hear me?
Yes, yes.
Can you see my screen?
Yes, yes.
So, good evening, everyone. I will discuss about the population inversion and entanglement in single and double glassy James Cummings model. This work is done with Sritama Dash, Professor Aditi Shende, and Professor Ujjwal Sen. We have shown that what is the effect of disorder on the population inversion and entanglement in single and double glassy James Cummings model. So, why disorders are so important? The first reason is they are everywhere, we cannot avoid them. And the fabrication of a perfect cavity with the atom sitting at a locked position inside the cavity is quite challenging. And there are possibilities of fluctuations in tuning the components of the setup, and so disorder may arise. This is the Hamiltonian of a single James Cummings model. This is the atom cavity interaction term, and G is the coupling constant. In this, there are many types of fluctuations, and in this paper, we have considered quench disorder. If the equilibration time is much larger than the relevant observation time of the disorder parameter, then the disorder is called quench disorder. And if the quench disorder is present in a system, then the system is called a glassy system. So this is the interaction Hamiltonian of our glassy James Cummings model. We have chosen our disordered parameter delta with the coupling constant G. This is justifiable because if there is any fluctuation in the position of atom, so there can be arise a fluctuating G. For ideal case where disorder is not present, this is the plot of population inversion with respect to time, and in this plot we can see there are successive collapse and revivals in population inversion. Here we have shown the atom-photon entanglement as the von Neumann entropy of entanglement, and we can see that entanglement oscillates from 0 to 1 for very small time, and for a later time it goes nearly to the maximally entangled situation. Now, in presence of Gaussian quench disorder, the collapse and revival phenomena, we can see there is a very strong suppression of amplitude of the revivals. And this suppression is exponential. And for entanglement, this is the feature. And for entanglement, it oscillates, but for a later time, it goes to the maximally entangled situation, where for population inversion, it goes to the almost zero. So the effects of disorders are, we have considered here 4 disorder distribution: Gaussian, uniform, discrete, and Cauchy-Lorentz. Only Gaussian is shown here. For uniform disorder case, we can have a strong suppression, but the suppression is not as strong as the Gaussian case. And for Cauchy-Lorentz disorder, the results are similar with the Gaussian case. But for discrete disorder, discrete coherence disorder provides the highest robustness to the phenomena of collapse and revival of population inversion as well as entanglement. And disorder may remove the phenomena of collapse and revival in population inversion of time evolved state of single James-Cummings model. But atom-photon entanglement continues to oscillate appreciably for a long time. Now, I will move to the double James-Cummings model case, and this is our Hamiltonian of double James-Cummings model. Here we have shown the atom entanglement, and the measure of entanglement is concurrence here, and we can see that entanglement abruptly goes to 0 at a point, and in that point entanglement has a non-continuous derivative, and the entanglement remains 0 for a finite interval of time. This abrupt vanishing of entanglement is called entanglement sudden death. And here if a Gaussian coherence disorder is present in the system, then this is the phenomena of Gaussian coherence disorder of entanglement sudden death, and we can see we can wipe out entanglement sudden death in presence of Gaussian coherence disorder. If we increase the disorder strength, we can wipe out the entanglement sudden death faster. This is the plot of the region bounded by atomic parameter alpha and the disorder parameter sigma A and sigma B, which is the standard deviation of delta A and delta B. This delta here we have taken delta A for GA, a disorder parameter with GA, and delta B for disorder parameter with GB.
You have 1 minute left.
Okay. This region is for that region where we can where we have the entanglement sudden death, and for the white region, larger region, we can wipe out the entanglement sudden death. So Gaussian coherence disorder is a good choice for wiping out entanglement sudden death. And for the other disordered case, uniform disorder is also good, but not as good as Gaussian disorder. And as previously we have shown that discrete disorder is more robust to these phenomena, and in this case it is also applicable. And for Cauchy-Lorentz disorder, here we can show that here is a quantitatively there is a major quantitative difference between the Gaussian case and Cauchy-Lorentz case. Here it is not shown, but it is shown in the paper. So the conclusion is entanglement sudden death can be wiped out by disorder, and different disorder distributions can induce significantly different behaviors, at least qualitatively. So these are the references. Thank you.
Thank you. So let me see the question. So we can have one question.
Hi, Ohana. Yeah, I had a question.
Yes.
Can you hear me?
Yes. Yes, I can.
Yeah, I actually had 2 questions. The first one is, what is your photonic field in the first part?
Okay, photonic field here is a squeeze state where is a coherent state of photon. This is Cn. I cannot show, but I can. Okay, I can say it's a in 0 to infinity Cn in Kate.
Oh, okay, it's a coherent state.
It's a coherent state.
And then you trace out the optical field and just
photonic part. I trace out, and then I will get the atom photon entanglement.
Yeah, and in the second part, like I can see that you have one atom inside each cavity, but how are they coupled to each other?
Okay, initially we have taken taken an entangled state, which is cos alpha 1 plus sin alpha 0 0. This is the entangled state. Initially this state is entangled. So in this way they are coupled, but they are not interacting with each other. The atoms are not interacting with each other.
They are only interacting with the cavity. Atom A is interacting with cavity A and atom B is interacting with cavity B. And they are isolated from each other, but the initial state is entangled.
Okay.
Thank you.
Okay, so if there's no more questions, so we thank Hannah, and we move to our next speaker. Next one is Baljit Kaur from Shiksha or Anusandhan. So Baljit Kaur, you can unmute here.
I think Baljit Kaur is not here, so I think we go to the next speaker. Because I don't see any Baljit Kaur in the list of participants.
He was here, actually. I have seen him. Maybe his internet was bad or something.
Yeah. We can go to that talk later on. We can go to now the next speaker, which is Kathakali. Kathakali, you can share the screen. I think you have already have.
Okay, so it will disconnect it. So now I'm back.
Am I audible now?
Yeah, you are audible.
Yes.
Yeah, it's full screen now.
Not yet, not yet. We see a folder only.
Okay, I already make it full screen.
Yeah,
No, but we cannot see your screen. I mean, we can see your screen, but not your talk. I think it is frozen. Maybe you stop sharing and share again.
Okay.
Yes.
Now?
It's the same place. We see your folder. I think you are showing us the wrong screen.
Hello.
Yes.
Hello.
Yes.
Hello now?
Yes.
Hello.
Do the full screen.
Yes, now?
Yes, someone is saying something.
Hello, ma'am. I'm Baljit. So I had some issue with my network. So now it is working.
Yeah, so maybe after Kathakali, you will present. Just wait.
Oh, my full screen is showing.
Hello.
Hello, Baljit.
Hello.
Hello, Baljit.
Yes, ma'am.
Yeah, you can present after Kathakali.
Yes.
Kathakali is starting.
Okay, ma'am.
Okay. So Kathakali, go ahead.
My screen is visible now?
Yeah, you are visible, but your voice is very low. So come close to the mic.
And now?
Yes, better.
Okay. Thank you, organizer, for giving me the opportunity to present our work. So our title of my poster is Entanglement and Other Non-classicalities in Various Types of Generalized Binomial States. So here we use a particular type of generalized binomial state, which is called NGBS, New Generalized Binomial State, first introduced by Lee. The reference is given in reference. So this state, by changing parameter, we can get binomial state, Fock state, coherent state from this state. That's why we called it generalized binomial state. So here we study various kind of non-classicality like anti-bunching, higher order anti-bunching, squeezing, Hong-Mandel and Hillary type, higher order Sapir-Whorf photon statistics, Agarwal-Tada criteria, and Vogel criteria. So to check this all non-classical criteria, we have to calculate the moment. So this is the expression of this moment. By using this, we study all these criteria. So here is the result. So A is for higher order anti-bunching. B here is higher order subpoisonian photon statistics. This is Hillary type quizzing. This is Agarwal Tara and Vogel criteria. So we can see that for the particular range of P, which is probability, we get the non-classicalities. So NGBS is highly non-classical state. And next, we have studied the entanglement for two-mode NGBS. So the entanglement criteria are SB criteria, SU11 algebra-based criteria, EPR entanglement criteria, and two-mode anti-bunching. So for two-mode so again, for all the study the all criteria, we have to calculate the moment. So here we have calculated the generalized form of moment. So here you can see that Cn. So Cn here is a coefficient. So any kind of two-mode qubit, you can study all non-classical criteria and entanglement criteria by this expression. So here we study the two-mode NGBS. From result, we can see that two-mode NGBS showing entanglement and also showing higher order anti-bunching. Yeah, and there is also a comparison study for all criteria. And yeah, so in poster it is showing elaborately. Please go to my poster and if any questions. Thank you.
Okay, thank you very much. If there are some questions, I mean.
Yeah, I have a quick question. Kathakali Shaptoshi here. So I just wanted to ask that when you're considering this two-mode generalized binomial states, and then reporting some non-classical properties like entanglement. So these so in the two-mode pure state sector, so this is sort of local unitary equivalent to a two-mode squeezed vacuum, right? So we have to just find out if you just try to think that there is just one parameter R and it captures everything. If you write the Smith form of it, am I saying it correct?
We didn't study here yet. Two-mode squeezed vacuum. We study here is. I can't understand your question. Please explain again.
Oh, sorry. Maybe we can talk later.
Okay, we can talk.
Just saying that so this state is locally unitarily equivalent to a two-mode squeezed vacuum. So the non-classical properties like entanglement should not change. So I just saying that. Okay, we might.
Okay, I can connect you later. I need some more research to, I think, answer your question.
So if there is any, I cannot see any more question. If there is some more question, please.
Yeah. Can I ask one small question?
Yeah. Sure. Go ahead.
Yeah, Kathakali, thank you for the talk. Could you tell me, like, these kind of states, how can they be created in the lab? Or is it just
There is a paper. Actually, we are studying this, but we can't. By Beam splitter, we can create a two-mode state, but not sure. I mean, have not experimented yet.
And some of the thing is like, is two-mode anti-bunching actually related to entanglement, or can it be independent of each other, right?
Independent each other. Maybe we can for different states we can get anti-bunching, but we don't get entanglement.
Okay, yeah. Thank you. Yeah.
Okay, then we move to next speaker. Yeah, thank you, Kathakali. So next one is Baljit Kaur
Yes.
from Shiksha. Yes.
Yes, sir. Am I audible?
Yes, yes. You can share your screen.
Okay. Okay, shall I start? So, good evening, everyone. The title of my poster presentation is Energy, Particle Nature and Fermionic Character as Signatures of Information for a Self-Gravitating System. Basically, I am studying this system having n self-gravitating fermionic particles, then calculate energy for this system, study particle nature and then apply it to black holes. So, the way of calculation we are doing is quantum mechanical approach using Newtonian quantum gravity, which is different from general theory of relativity or quantum field theory of relativity, which we can see from this cube of physics. So this is the Newtonian quantum gravity approach which we are using. So suppose if we take, suppose if we see from general theory of relativity equation, so from general theory of point of view, the energy momentum content of the system is represented as the language of curvature of space-time, and there is no way to study the particle behavior of this system. But coming to our Newtonian quantum gravity, using Hamiltonian for n self-gravitating system, we can calculate exact ground state energy for the system. So this is the main motivation to work on this Newtonian quantum gravity, and we can say these are the two different representations to treat the system. And here one more interesting point is there, that as the energy is not well defined in general theory of relativity, but we have the exact energy, but both provide the same formulas for Schwarzschild radius and Hawking temperature when applied to black holes. So the ground state energy I have found for this system is using density functional theory and taking a trial density. So the kinetic energy I have used is in Thomas Fermi approach, and the potential energy is the direct term. So using this thing and minimization, I found the total ground state energy for the system, which successfully satisfies the virial theorem. Now, then we special relativize the maximum velocity of a particle within a star, and using this we define the radius of a neutron star and found the Schwarzschild radius for our system, which is found to be 2gm by c square. So we can get critical number from this value, and once we have the critical number, we can calculate the critical mass for a neutron star. So as this system I am treating is a fermionic system, so there is an effect of exchange correction to the system. So incorporating this exchange correction term to the Schwarzschild radius, we have the Schwarzschild radius with these corrections. Then I have also derived the Hawking temperature. So the energy, using energy required for the creation of a particle-antiparticle pair near the event horizon and taking the uncertainty principle for n particles, I have derived the Hawking temperature. And again, this is the fermionic system, so I have added the exchange correction term also. Then coming to exact energy, what we found here gives the exact value for a system of n self-gravitating fermionic particles. This exact value successfully satisfies the upper and lower limit for any n given by Levi-Levelin and gives the exact energy value for two particles. And if we see, we have calculated for large n. So for large n, it correctly reproduces the Hawking temperature with its numerical coefficient 1 by 8 pi. So from this graph, we can see that our exact energy system is satisfy both the upper and lower limit given by level epsilon. So now coming to conclusions, so from this talk, I found that the exact energy, exact ground state energy for n fermionic self-gravitating particles, then derived Schwarzschild radius and Hawking temperature for this system. And these are the references I have used. So thank you.
Thank you. Thank you so much. So if there are some questions, please feel free to ask. Okay, it seems like there's no question. So thank you, Valjit, for a nice talk.
Thank you.
Okay, so now this is the end of this poster session. So maybe I ask Professor Aditi to maybe tell the next event,
Yeah,
which is a keynote speak. Yeah.
Yeah, so thank you very much to all the afternoon session speakers and poster presenters, and also thank you, Arun, for chairing this session.
Thank you.
So we have a kind of 45 minutes break, but this Zoom link will be open, so people can ask questions, look at the posters, can discuss. And around 7:20, we come back for the next sessions, which will be the talk by Professor Anna Sanpera, so the first keynote speaker, and we will come back. Thank you. Chandan. Hello, Chandan.
Yes, ma'am. Yeah.
Yeah, I think you can off the online streaming, right?
Okay, fine.
Because, otherwise, just 1 hour there will be a.
Yes, sure.
So you can start around 7:20, but maybe this Zoom link is created, so it should be on.
Sure, this will be active. Okay.
Yeah, it should be active. Okay.
Yeah. Oh, fine.
Yeah.
Hi, Aditi.
Hi, Himadri.
Hi.
Yeah. Okay. Hi, Himadri, I have to tell you that you are chairing the session, the similar poster sessions on 15th.
Yeah. Last day, I saw that. Yeah.
You don't have.
I wanted to ask, where are the posters kept?
Yeah, it's in the schedule. You go, you click on the name, and it's all there.
It's on the